Welcome back. So, in today's lecture, we will highlight the importance of surface. By taking, let's say, one particle with a radius 1 centimeter, we will try to cut this particle or object into several halves down, and we'll demonstrate that how by cutting this sphere into several halves down, how we can increase the surface area, how we achieve or how we obtain the larger surface area. That aspect we will show in this video lecture. And apart from that, we will also discuss something about what is specific surface area for a given object, how we can calculate. And we'll also try to highlight on the importance of surface chemistry from various applications, right? So now we will move on to the first topic, that is surface, importance of surface, right? As you can see here, we are going to do one simple exercise. Let's say we take a simple object, spherical object, which is 1 centimeter in radius, right? If you want to calculate what is the volume, because we have only one spherical object, the volume of it we can calculate, okay, using the formula 4 by 3 pi r cube, and then we now know that we have got only one sphere, okay. So area per sphere can be calculated for this one sphere, that is 4 pi r square. Now, by multiplying this number of sphere into area per sphere, we can actually calculate what is the total surface area or total area, right? Now, in the second step, what I'm going to do is, I'm going to cut this spherical object into two. Instead of one radius, 1 centimeter, radius, we will now have the radius as 0.5 centimeter. In this way, you will achieve number of spheres as 8 because your volume per sphere goes down drastically. Now, when you calculate the area per sphere, it is again lesser than what we obtained in the previous case. But if we have to achieve total area, we need to multiply this area per sphere into number of spheres. You look at this one, because the number of spheres has gone up. So when we multiply these two value, you get the total surface area, which is at least 2 times higher than the previous one, right? So the same exercise, if we have to do, okay, keep cutting these objects several halves down, you will reach some point wherein you will go from a macroscopic object into a microscopic object, and even sometimes you will go up to the dimension nanometer in size. So you can see that although the volume, which is nothing but the volume per sphere and the number of sphere is same in this case, because the number of spheres has gone up too high, right? And although the area per sphere is significantly smaller in this case, you can see that when we multiply these two, we get the surface area, which is at least 9 orders higher than the original one, right? So we started with surface area as 12.56 centimeters square, but now we have at least 2 into 10 power 9, right? So which is at least 9 orders greater than what we have had initially, right? So what it comes to say is that when we cut this sphere into several halves down, when we approach the size almost nanometer or micron size, your the surface to volume ratio goes up significantly. Okay, so this comes to say that for small particles, the surface is very key, right? It is a key aspect, right? So here we look at a simple, exercise for a specific surface area. How will you calculate specific surface area for a given object? Let's say we start with a spherical particle, right? So specific surface area is defined like this. It is a ratio of total surface area to the total mass of the sample. Let's say if you collect handful of sample containing spherical objects, okay, you need to know what is the radius of the particle, okay, and what is the mass of the sample. So once we know that, we can actually calculate what is the specific surface area of a given geometry. In this case, since we know that the area of a sphere can be calculated by knowing the radius, but then we need to multiply that with n number of particles that we have in the sample. So in this case, you have n 4 pi r square simply. And in denominator, so we can multiply this by multiplying volume into density, bulk density, we will achieve the total mass of the sample, right? So since volume is in this case 4 pi r cube, we can also multiply this quantity with number, because there are number of spherical particles. In this way, you will get a compact equation for sphere, that is 3 by rs rho, by knowing just the radius and bulk density of the particle that we deal with in the sample. One can get what is this specific surface area for a sphere. Okay. Now, just to appreciate the difference in surface, we will now deal with let's say cylindrical particle. Maybe you're working with, let's say, carbon nanotube particles or rod and silica rod. There are various particles you may be dealing with. Let's take an example of cylindrical object, right? In this case, how do we calculate the specific surface area? Remember, this cylinder is not hollow. Okay, when you synthesize this kind of a particle, you will also have this surface is also be filled, right? So in this case, you will have the surface that is coming out of the as part of, the length and both the radius will be taken into account in this case. So you can see that the specific surface area we can calculate for this case in this way. Okay, so let's say I have to calculate the specific surface area for this case. Now all I need is, I need to know what is the surface along the length, right? 2 pi r L, right? 2 pi r L, okay, plus we have got two sides, right? So both side carries area of pi r square, so we will have 2 pi r square, because we got two ends over here, and the denominator we have to okay, this entire thing has to be multiplied with n, because we have got n number of particles. In denominator we have similarly, so here we will have to multiply volume with rho, right? Rho, and then we have number of particles. So these two can be cancelled out. Now I can take 2 pi r common, and then I have L plus r ultimately. Then I have pi r square. Then I have L into rho. So I can cancel this common term. So then I will have simply L plus r, okay, divided by r into L into rho. Okay, so this I can write as also, then you have in numerator you have 2 also, right? So we can write this as 2 by rho into 1 by r plus 1 by L. This is my compact equation for cylindrical particles. if you want to calculate the specific surface area, you can use this approach, right? In this case, we need to know what is the radius of the particle and what is the length. For example, if you're dealing with a thin rod, maybe a wire, cylindrical wire, there the length will be important compared to the radius, right? Because radius will be too smaller. In that case, you can ignore this one. For a thin rod, you simply have 2 by rho L. Okay, for this kind of a particle where radius is very important, length is insignificant. In that case, you will have 2 by rho into R. This is for thin rod, and this one is for disc. Okay, so in this way you can calculate the specific surface area. Now we will move on to the impact of surface chemistry. Okay, maybe from different perspectives, different applications point of view. So let's first take an example of the biological and life sciences applications. For example, biological membranes and cells. Now we know what is known as liposome, micelle, bilayer sheet. These are self-assembled structure of lipid molecules. You may have seen this term micelle whenever you dealt with the surfactant, right? Surfactants are known to form micelles. Okay, when they form micelles, because surfactant has got two components into it. One is hydrophilic group and another one is hydrophobic part. Now this tail, which basically is nothing but hydrophobic part, whereas the head group is hydrophilic, right? So if I look at this micelle, a simple structure, it has got at the center, it can actually entrap organic molecules which are not water loving, right? The affinity towards oil-like substances will be very high in the case of micelle. So it can trap organic molecules, right? Example, you can use this kind of, this kind of structure is very useful in oil recovery, right? Enhanced oil recovery and things like that. Then the liposome are also called as surfactant capsule. Okay, this was discovered way back in 1960. Okay, both liposome and bilayer sheet both are actually bilayer structure. Okay, they self-assemble to form bilayer assembly. Whereas in liposome, this is spherical in shape, whereas this one is sometimes cylindrical or rectangular. Now, if I look at this structure, it has got a unique way of encapsulating the cargo molecule. The cargo is a vehicle that carries the drug, right, along with it. So liposome can be used as a drug delivery vehicle because it can actually encapsulate the drugs in 3 different ways. One is it can encapsulate the drug molecules into the core, which means that hydrophilic like drug molecule or cargo can be trapped in this core part. Whereas outer side, again, you can actually get this cargo molecule attached to this outer the exterior part as well of this liposome, and then inside between interior and exterior part you also have the tail group, which is basically nothing but a hydrophobic part. It can also trap hydrophobic drug cargo or drug molecules, right? In this way you can encapsulate drug and deliver, use it as a drug delivery vehicle. One of the the advantage of using liposome is that it can deliver the drug into the target area, okay, selectively. The advantage of that is it can help us prevent from the side effects. generally when you consume drug in the free form, in a conventional way, what happens is because it is also creating some sort of toxicity to the areas of the body that are not affected by the disease. So not only it delivers the drug into the conventional drug delivery system doesn't work effectively because it is also delivering the drug into the area which are not affected by the disease, right? Whereas this liposome, it is possible to employ liposome as a drug delivery vehicle, which will not be detected by the hunters, or you can say macrophages in the body, so that the drugs can be delivered to the cells effective manner. Okay, this is one of the important applications from the biological and life sciences point of view. Here, surface is very important because the hydrophobic interaction between the liposome and drug molecule, okay, or even hydrophilic, the affinity between hydrophilic part and hydrophobic part is very important because when we deal with surface, so these interactions also very important that we will study as we move on, right? So next is the surface chemistry from the imaging device point of view. So gone are the days where we used picture tube in TVs, right? Nowadays those picture tubes are replaced by liquid crystal device, okay, LCD. And another example of flat panel device I can give is this one, electrophoretic imaging devices. Okay, it contains it contains simply the TiO2 nanoparticle, submicron size nanoparticle. Along with it, there is also a dye molecule which is spread in the matrix, right? So the TiO2 is basically help in providing the a good contrast when we weave it through the weaving plate, right? And the dye molecule absorbs some light so that it can provide perfect balance between the light that has more brightness, and it can also tune the contrast of the imaging, right? So the dye molecule here is to provide the contrast, whereas the TiO2 is to provide the high optical contrast under even normal lighting. Okay, so the reflective property as well as the absorbing properties both are coupled together in this application, right? So this together they provide a very high optical contrast even under normal lighting. So this technology is nowadays used extensively. So it has replaced the conventional system of picture tube, right? But then still we do have some challenges when we deal with this kind of technology. Like for example, when we use higher concentration of particles, there may be the stability is an issue. They will aggregate. There's a tendency for these particles to come together and aggregate, and so then the stability is a big question that one has to address when we deal with this kind of an application. Here, surface chemistry play a very important role. When we talk about stability, the interaction between the particle and dye molecule, right? Their electrophoretic mobility also is affected by the TiO2, the property of TiO2. So all this becomes very important when we deal with such application. So this is from the again we have another application from the the groundwater perspective. Let's say we know that the groundwater table is often refreshed. Often treated using some reagent, to remove the contaminants from the bed, right? So let's take an example of in the water table we have rock, right? Porous media, right? Into this porous channel there will be contaminants sometime, right? They settle down over the period of the application. Now this colloid, sometime people use this for example, if you want to remove the contaminant which is hydrophobic in nature, people often use colloidal particle which is also hydrophobic, so that when we use it to charge the porous media, so this colloidal particle can combine with the pollutants, right? Combine with pollutants, and then they can these pollutants can get attached with the colloidal particle, and then it can the solid. I mean the pollutant molecules can be easily transported, okay, removed from these bed, right? So this is a very important application based on the colloidal nanoparticles or colloidal particles, right? So the next application that we will see is metal organic frameworks. Here also, we will look at the application from the point of surface to volume ratio. So basically, this MOFs, which is metal organic framework, is often used. I mean, it took a center stage in recent time because of its capacity to absorb, right, the hydrogen or CO2 molecules, right, in a significant amount, right? For example, it is light in the advantage that we have here is it produces lightweight and compact materials. Okay, we can use this material to absorb or dissolve large amounts of hydrogen. Okay, because it contains three-dimensional network porous structures. Okay, these structures are formed by what is known as metal and organic framework. The metal atoms are linked with the organic ligands. Okay, and this structure provides a greater capacity for storage. Okay, and it offers a high surface to volume ratio. These MOFs can be prepared in a different shape as well. But what is so unique about this structure is it forms honeycomb-like structure, wherein these metal atoms are connected with the organic ligand, and because it provides a three-dimensional porous structure, the storage capacity, the absorption capacity is also increased several fold. Okay, so these are various applications considering the surface chemistry from different perspectives. We have seen biological perspective, and we have seen from the metal organic framework perspective, okay, and imaging devices perspective, and water treatment perspective, right? So there are, we can even go on listing many such applications, but we'll stop here. We will continue from the next lecture. Thank you.